Now that we are familiar with our inverse trigonometric functions, we can now consider compositions of trigonometric functions. Recall from college algebra that the composition of a function f and g is denoted as f composed with g of x, and this simply means that we have one function plugged into another function. It's a function evaluated at a function. In example 4, we'll practice embedded or composed trigonometric functions. We want to find the exact value of each composition without using a calculator. As we do this, we always need to consider the range of our inverse trigonometric functions. So on example A, we're going to evaluate tangent of arc cosine of 1/2. When evaluating a composition, we always begin with the innermost function. So first we need to find arc cosine of 1/2. Recall that the range of arc cosine is an angle between 0 and pi. That is an angle in quadrant 1 or quadrant 2. Because the value of cosine is positive, we are looking for a quadrant 1 angle. The angle in quadrant 1, whose cosine or x-coordinate is 1/2, is pi over 3. So I'm going to replace arc cosine of 1/2 with its value pi over 3. Then we can evaluate tangent of pi over 3. Recall that tangent is evaluated as the y-coordinate divided by the x-coordinate. So on our unit circle at pi over 3, the y-coordinate is square root of 3 over 2, and the x-coordinate is 1/2. Now, if you have that value memorized, you can skip this part here and jump straight to the result of square root of 3. That's the exact value, but it's always a good idea to check with a calculator. So let's verify this information. Now, my calculator is in degree mode, but because we are going from an angle back into a tangent function, it's not going to matter which mode we're in. So let's evaluate tangent of inverse cosine of 1/2. The calculator is going to spit out the value 1.73. And if we compare that to our result, square root of 3, we can see that the decimal values match. We would get the same results if we were in radians. Let's try example B. This time, on the inside, we have an ordinary trig function, and on the outside, we have our inverse trig function. So we'll start by evaluating that inside function. Recall that sine of pi over 2 is equal to 1. Now we can evaluate inverse tangent of 1. Let's review the range very quickly for inverse tangent. Recall that inverse tangent spits out a value between negative pi over 2 and pi over 2, or an angle in quadrant 4 or quadrant 1. Because this ratio is positive, we know that we're looking for an angle in quadrant 1. So we need the angle in quadrant 1 whose tangent is equal to 1. That one's an easy one. I hope you like that one like I do. That gives us pi over 4. Let's change our calculator to radian mode for this one. And then we can evaluate inverse tangent of sine of pi over 2. And we end up with 0.785. Let's compare that to our radian result, also 0.785. So we've done a good job evaluating that one. Let's try secant of inverse sine of 1 over the square root of 2, beginning with our inside function. Recall that the range of inverse sine is from and including negative pi over 2 to pi over 2. So we need an angle either in quadrant 4 or quadrant 1 whose sine value is positive 1 over the square root of 2. Sine is positive in quadrant 1. So I'm looking for a quadrant 1 angle whose sine is 1 over square root of 2. Or if you recognize, when we rationalize that, it's square root of 2 over 2. That's going to give us pi over 4. Now, if you answered in degrees here, you'd still get the same final result. To evaluate secant of pi over 4, of course, we're going to evaluate 1 over the x-coordinate. The x-coordinate is square root of 2 over 2. When we invert that, we're going to get 2 over the square root of 2. And you can either rationalize here or recognize that 2 divided by the square root of 2 is the square root of 2. So let's check this one also with our calculator. To evaluate secant, we're going to type that in as 1 divided by cosine of inverse sine of 1 divided by square root of 2. It almost takes as much talent to get it into the calculator as it does to just evaluate it directly. And comparing that to our exact result, the decimal values match, so we can be confident that we've done it correctly. Let's try example D. Inverse cosine of 3 pi over 2. Notice we have 2 successive inverse functions evaluated right in a row. Generally, when you evaluate 2 successive inverse functions, they undo each other's operation and you just get the argument. You may have remembered this as being stated in college algebra as f of f inverse of x equals x, and vice versa, f inverse of f of x equals x. However, it's not quite that simple with our inverse trig function. The range of inverse cosine complicates things just a little bit. Let's start with evaluating our inside function. That's going to be pretty straightforward. Cosine of 3 pi over 2 is equal to 0. Now we need to evaluate inverse cosine of 0. Recall that the range of inverse cosine is an angle in either quadrant 1 or quadrant 2, an angle between 0 and pi. The only angle between 0 and pi with a cosine value of 0 is not 3 pi over 2, but pi over 2. Definitely a candidate to check with our calculator. I am in radian mode here, so I'm going to evaluate inverse cosine of 3 pi over 2. And we come up with 1.57 approximately, which is equivalent to pi over 2. Now, this is not always the case for every angle. For example, if I did inverse cosine of a quadrant 1 angle, like pi over 4, the inverse cosine and cosine are going to cancel out, and notice it yields the argument pi over 4. So again, paying close attention to the range will help you catch those special cases like example D. Example E, we have sine of inverse cosecant of -2. Recall from the previous section that we can evaluate inverse cosecant in terms of inverse sine. We do this by reciprocating the argument. So we need to start by evaluating inverse sine of -1/2. Let's pay careful attention to the range of inverse sine. Recall that inverse sine spits out a value between -pi over 2 and pi over 2. Because the ratio here is negative, we're going to be working in quadrant 4, but I want to make sure my angle is between -pi over 2 and pi over 2. So the angle in quadrant 4, whose sine is -1/2, you may think of it as 11 pi over 6, but we need to express it as -pi over 6 so that it fits into the range. Then sine of -pi over 6 comes out very nicely to be -1/2. So in this case, the outside and inside functions do cancel and the argument is the result. But again, let's verify this with our calculator. We will type this in as sine of inverse sine of -1/2. And we obtain -0.5, which is equivalent to -1/2. Let's finish with tangent of inverse tangent of pi. This one's a little bit tougher because notice the input to our inverse function looks like an angle, but we know that the input to an inverse function represents a ratio, y divided by x on the unit circle. So let's make a quick glance at the range of inverse tangent. Recall, it's very similar to inverse sine between -pi over 2 and pi over 2. If the input is positive, then we know that we're working in quadrant 1. If we're working in quadrant 1, then tangent of inverse tangent is going to yield an angle in quadrant 1. That is, whatever the value of inverse tangent of pi is, tangent of that result is going to give us pi. Let's definitely verify that one with our calculator. tangent of inverse tangent of pi gives us 3.1415, which of course is pi. So that one's tricky because, now really think about this, the input to an inverse function is a ratio, but it looks like an angle here. All right, let's take this one step further and evaluate these compositions algebraically. So on example 5a, we have sine of arc cosine of x. Notice in this case, the input is not a number, but an algebraic expression. And we're going to be able to simplify this using the trick of SOHCAHTOA. Let's start with the inside function, arc cosine of x. Now the input to that function is a ratio, and the output is an arc or an angle. So I'm going to say let theta represent whatever angle comes out of this arc cosine of x evaluation. Now if theta is equal to arc cosine of x, we can also recognize that is inverse cosine of x, just using different notation. This means that cosine of theta, ordinary cosine of theta, gives us x. Let's imagine theta as an angle on a right triangle. So I'm going to put theta here. This is a right triangle. Cosine is adjacent over hypotenuse. Well, I can think of that x as x over 1. So the adjacent side would be x and the hypotenuse would be 1. We can then figure out the vertical segment of this right triangle. I'm just going to call it b and apply Pythagorean theorem. We have x squared plus b squared equals 1 squared. Solving for b, we can see that b squared is 1 minus x squared, or b is plus or minus square root of 1 minus x squared. Since we're using b to represent a length of a right triangle, we will use the positive square root only. That is, this side has a value of the square root of 1 minus x squared. Now, back up to our original problem. We were trying to find sine of arc cosine of x. We let arc cosine be represented by theta. So we need to actually find sine of theta. Now remember, theta is represented on this right triangle. Sine is opposite over hypotenuse. So now we can say algebraically that sine of theta is simplified as opposite square root of 1 minus x squared over hypotenuse 1, or simplifying this down to the square root of 1 minus x squared. Whew, that was a lot to think about. It's probably worth it to practice that a couple more times. Once again, on example B, we're going to evaluate the inside function first. So the inside function is an arctangent function. This means that the input is a ratio, but the output is an angle. So we're going to recognize that. Theta makes us think of an angle. So let's suppose that theta represents the angle that comes out of this arctangent function. Recognizing that arctangent is the same thing as inverse tangent, you can skip that step if you want to, I'm just doing it for clarity. We can then see that tangent of theta is equal to x. Well, let's suppose that theta is some angle on a right triangle. Tangent of theta is equal to x, or we could call that x over 1. Tangent is TOA, opposite over adjacent. Now, if we apply Pythagorean theorem, you can probably see that this side would be the square root of 1 plus x squared. A squared plus b squared equals c squared. We would take the square root of both sides to solve for that hypotenuse. Now that we have our triangle set up, we can come back to our original problem and say cosine of, remember, arctangent of x, we represent it as theta. And cosine of theta from our right triangle would be adjacent over hypotenuse, or 1 over the square root of 1 plus x squared. All right, that's a pretty detailed problem, so we're not going to worry about rationalizing the denominator. We will leave it as is and be happy with that. Now, once you learn the process, it's really pretty simple and repeatable. This is something that you'll see when you get to Calculus 2 in a process called trigonometric substitution for evaluating integrals. This part will be a smaller problem within that larger process. So this is very useful. Don't overlook it. It helps if you master this skill now, and you'll be prepared for the classes that come in your future. So let's try this process one more time. We're going to start by examining our interior function, which is an inverse function, right? Remembering that the inverse function yields an arc or an angle. We'll say theta represents this inside angle. You can call it alpha, you can call it beta, take your pick. Recognizing alternate notation here, this is the same thing as that inverse sine function. This means sine of theta must be equal to x, or we can think of that as x over 1, because we're going to put theta on a right triangle like we've been doing, and we're going to recognize sine of theta as so, opposite over hypotenuse. Then we could solve for the horizontal segment. It's going to be very similar to our first triangle, except the legs have switched. So the horizontal segment is the square root of 1 minus x squared. Once again, we obtain that with Pythagorean theorem. Backtracking to our original problem, we need to find secant of arc sine of x. And remember, we let arc sine of x be represented by theta. So we need to find secant of theta. Okay, I'm going to drop down here. Secant of theta, recall, is 1 over cosine of theta. Have you noticed trigonometry is all about relationships, learning the relationships in between functions. Secant and cosine have that reciprocal relationship. From our right triangle, we can evaluate cosine of theta. Recall that cosine is ca, or adjacent over hypotenuse. The adjacent side to theta has a length of square root of 1 minus x squared. The hypotenuse, of course, is 1, so we can leave that off, keeping our fraction nice and simple. So there you have it. Secant of theta is equal to the 1 over the square root of 1 minus x squared. I don't know about you, but I think those are kind of fun. It's like putting a puzzle together. I hope that you agree with me, and that is also your idea of fun. So thanks for listening. I hope your homework goes well.